Un, deux.
All right, our next and final talk is going to be by Ambroise about category theory diagrams.
Okay, thanks for the introduction. I will start with a naming convention. I will refer to my editor as YAD for yet another diagram editor. It's not totally satisfactory because there is another software called yet another diagram engine. So sometimes I prefix it with CoReact, which is the name of NR project, which is about Coq-based rewriting towards executable applied category theory, in which I am involved. And there is, if you can check it, there is the website link on the slide. If you get bored during my talk, you can go on my website and try it online. Okay, how does it work? Maybe I should, because there will be a demo at the end, so I should first figure out how to show my screen. Display setting. Yes. Okay, it's not ideal, but we'll do like that. Okay. Okay, so this is my website, and you go here, and you get the you get the editor. This is the tutorial, and once you have read it, there is a small exercise that you can try. It's basically replicating this square, but without using the mouse in 4 actions. Okay, but this is not. Okay, let's come back here. Okay, so it also comes with there is also a standalone desktop version which embeds the web app using Electron, and it also comes with this. This standalone version comes with a mechanization feature that I'm going to describe in the following. But before that, I want to mention Quiver, which is another software for editing diagrams. It's also runs in your browser, so it's quite nice. I want to do a quick comparison with this editor. So it's about the same size in terms of lines of code. Quiver is mainly implemented in JavaScript, whereas my YAD is implemented in Elm, which is a functional programming language. Quiver is more user-friendly and have a lot of styling options. YAD has more editing features, so you have tabs, copy and paste, find and replace, or expand selection to connected components, kind of things. And in both cases, we have LaTeX export. But the main thing about YAD is that it comes with mechanization features. So I'm going to introduce them now. So to begin with, just to explain a bit the architecture, how it works, that you would run the editor in the background, the standalone version, and then you will also run Visual Studio Code with my custom VS Code extension, which builds upon the CoqLSP extension. And then there is also a Coq library for custom notations and for category theory. So what can it do? First, it can show, if you move your cursor somewhere in the file, it will show the diagram. It will show a diagrammatic representation of the goal or of the diagram if it's relevant. The other thing that it can do is that it can generate a proof. So you draw your diagrams and with you embed the proofs in the diagram, and then it will generate a proof script that show commutation of the outer diagrams. I'm going to explain a little bit more about that. With a simple example, even if you are not too familiar with category theory, there is a easy result that if you have one natural transformation, alpha from F to G, and another one, beta from G to H, then you can define the composite natural transformation. And so it means that this diagram commutes for all function morphism F. So saying that it commutes means that both branches here are equal. So if I compose H of F with beta C1 and alpha C1, which is this composition here, the left-hand side, then I should get the same thing as beta C2 composed with alpha C2 composed with F of F, which is the right-hand side. So the diagrammatic proof would consist in splitting this diagram in two sub-diagrams, introducing this intermediate morphism here, G of f. And then we know that both sub-diagrams commute, so this gives a proof of the commutation of the outer diagrams. And this can be turned into a computer-friendly proof somehow, just by applying rewriting rules. So here we use the fact that the right diagram commutes first to rewrite h of f composed with beta c1 into beta c2 composed with g of f, and then we use the other commutation to do the other step. Okay, so of course this should be automatable, and this is what YAD can do. I'll show you later. And another thing that you can do is that you can construct diagrams step by step. So I will be a bit more specific about what I mean by that. So the thing is, you start by selecting a sub-diagram here. And then you create a proof node in the editor. And you can give it the label a Coq tactic. So here we would say naturality, for example. And what happens is that Coq, in the VS Code window, will check that this tactic actually solves the goal. So what is this goal? It's the fact that h of f composed with n of a is equal to nb composed with a whole. So this is really, so you see this this arrow here is unnamed, so it will be converted into instantiation variable evar in Coq. And so after that, the diagram gets completed in the editor, because Coq is smart enough to guess what is the unnamed arrow, so it will rename the arrow accordingly, and also the proof node will be saved and marked as validated. So this is a green check mark here. So just before going to the demo, I want to mention another software for mechanization of diagrammatic proof, which is Luc Chabassier's interface. So it's another architecture. First, it's a standalone program implemented in Rust, and it's relies on a Coq plugin, which introduces a diagram server. And this Coq plugin can provide the interface with goals and assumptions and the available lemmas in context. And then the interface would produce a Coq proof term that will not show in your VS Code window. It will be implicit. But you can still do print proof if you want. So it's not really meant to be a diagram editor, so there is limited manual layout. And it's also nice because you have some graphical proof tactics. Okay, now I'm going to jump to the demo. So this demo is based on, so you can check it on, it's on the it's on GitHub. It's based on the category theory library of hierarchy builder, and I have also added some tactics and notations on top of that. So what is the example? So you all know that a distributive law between two monads induces the monad structure on the composite endofunctor. And we will show in particular that the inverse multiplication defined by this formula is associative. Okay, so okay, it's not on the right screen. I can't see anything. Yes, but I would like mirroring. Yes, I want that, but I don't know how to. Windows P, sorry. And duplicate then. But yeah, it doesn't work. So let's go back to the extension. Okay, so now I want to increase the size because I can't see anything. Yes. Okay, so, all right. Okay, so this is the file. Okay, I will put this here. Okay, so this is the category theory library. Is it okay? Can you see the screen? Yeah, okay. And these are my custom notations and tactics. So we introduce a category, C, 2 endofunctors on it, multiplications for those endofunctors. I will omit the units because we will only focus on the associativity. I introduce some LaTeX notation for those. And this is the associativity for the multiplication of S and T. So now here is a line with a diagram. So it's called the diagram. And then the data that you see is some JSON data. If I put my pointer on my cursor on it, it will load the editor and show it. But it's on the wrong screen, fortunately. Here we are. Okay, let's try to increase the size. Yes. Okay, so this is associativity for S, for mu S. So you see, it's, you have two ways to go from SX to S of X. And they must be equal. Okay. Now we have the distributive law here. And it must satisfy some compatibility conditions, which are here, mu T delta and mu S delta. And here is a graphical representation, a diagrammatic representation. So this is the first one, and this is the second one. I will save them for later, so I'll duplicate the tab, and I rename it as compat. Okay. So what's happened is each time when you move the cursor in the editor, it's only the first tab that is going to be updated. Then okay, so this is the definition of the composite of the multiplication for the, and this is what we want to prove here. Okay, so here I unfold the definition and I normalize to make it nice. And if you look at what we want to prove, here it is. So this is what we want to prove here. So I have already done the proof for you. Here it is. Nice. Okay. So let's duplicate this. I move this here. Okay, excellent. Up. Okay, so you see here, I have done the proof. I did my homework. All of these check marks are actually proofs. So if I edit them, you see, if I rename them, you can see that it's actually proof tactics here. It's embedded in a macro which is called CoqProof, which is like just a beacon for the editor to know that it's actually a proof. And you can change the appearance by updating the LaTeX preamble, which is here. But now, how do you know? So this is a proof. So it's just a diagram. So how do you know that it's correct? That actually the proofs are really validated by Coq. So there is a command in the editor to check to ask VS Code whether this proof is correct. And doesn't seem to work. Ah yes, maybe it's worked, but we can't see can you see that it's green now? Okay, because I can't. So yeah, so what happened is that if you look at the VS Code window here, there is this notification which says that actually it's a valid proof, and I can for example give you Whoa. What's happening? Okay, something strange happened, but okay. Here I will change it for reflexivity just to show you that it's actually not turning everything in green. So here I get it still remains black, and in the VS Code window you get the fact that it actually failed. Okay, so now how can you do this more interactively? Let's start from. Okay, I will just show you some features now. We'll start from the. Actually, let's start back from the beginning. Yes, it's ugly, but okay. Okay, so let's say you want to rewrite those two. There is a lemma that allows you can use compatibility of delta here to rewrite these two rows here. So I select those two rows, then I create a proof node. So it asks me for a proof. Okay, it's very small, but I'm writing I'm writing the tactic to apply the compatibility of delta with mu s. So what happened is that it has used it has called Coq, and then Coq has applied the lemma and then inferred that actually the other onside should be this. So you can go on like that. You can even do it more interactively. Like, for example, if you want to, what time is it? Yeah, okay, maybe I will just show you the generation of how you can generate the proof. So let's start from the proof that I have done at home. Save it in a new tab, and now I select the full diagram here, and I press the export command to Coq. And what is going on is that it's going to send it will generate a proof script and send it to VS Code, to VS Code, sorry. And VS Code, now if I look in the window, you see that it has generated a proof. So it has actually asserted all the subdiagram commutations and build a proof of the commutation of the outer diagram out of it. And it seemed so, because there's a lot of steps, so it's quite long. But it seems that Coq is happy with the proof. And what does it use? It uses some associativity tactic just to. So no, the associativity is just associativity of composition in categories, and there are also some lemmas like just congruence lemmas that are applied. And if you do not provide all the proof nodes, then it will just replace, for example, if this proof node was omitted, it will just add inserted admit tactic. Okay, I think I will stop here. Oh, okay, I have 2 minutes. I can show you something. Let's go back here. Well, okay, maybe I stop here because we are all tired. So, yeah, thank you for listening.
Thanks for the talk. Do we have questions?
how terrible can the categorical proof become? Can do things like 2 categories, or is this just normal, simple, nice 1 categories?
It's only simple, nice categories. But you are free to draw two categorical diagrams if you want. I'm doing this sometime during the weekend, but there is no mechanization support for that.
Okay, thank you.
I go, just very simple question, Ambroise. Do you think there is interesting for you to run your editor inside VS Code, or you think it's better as a separate application?
I think it would be nicer to be in VS Code because then maybe it could be available in the web version of VS Code. But I think it will be also a lot of engineering to make this work. So I'm not sure it's worth it.
If I have my own category theory library, can I wire that up with your tool, or do I need to use your category theory formalization?
What you need to do is to define the tactics and notations so that it works. So I can show you the file that I've been actually written to wire it to the category theory library of hierarchy builder. So you need some notation like this, like just custom notations associated. You need to provide those lemmas. They are very simple, but just this is because these are lemmas that are generated, that are used in the generation. In principle, it could be made more parametric, but so far, yes, it works like that. But yeah.
So let's thank our speaker again.